Welcome to this presentation on illustrative motion smoothing for attention guidance in dynamic visualizations. My name is Johannes Eschner and I'm presenting work conducted together with Peter Mindek from Nanographics and Manuela Waldner from TU Wien. Animations have been shown to improve learning performance for learning about complex processes such as molecular biology. However, producing these animations is challenging because of the complex, cluttered and chaotic nature of the scenes depicted, as can be seen here in this example from biology. Animators have adapted different techniques to overcome these challenges and guide user attention towards the areas which need attention at that moment. One example would be to highlight the focus elements of the scene by visually emphasizing them. Alternatively, it's also possible to low-light the context elements, thereby guiding the focus to, for example, this molecule here in the scene. A combination of multiple such techniques can also be employed to even further emphasize the focus on a certain element. Natural camera features, such as depth of field, are also often used to naturally focus on a certain element of the scene. Motion blur would be another such natural camera phenomenon, which could be used for dynamic scenes where the fast-moving objects can then be blurred and therefore be slightly suppressed in the context of the scene. We propose to implement illustrative motion smoothing as a technique to remove high-frequency motion in the context to focus on the high-frequency focus elements which are not smoothed. For our illustrative motion smoothing, we implement two different motion smoothing strategies. The first one is called geometric motion smoothing, where we modify the trajectories of the scene elements to give them a more smooth appearance. In this figure, you can see that the original trajectory of the element is more jagged than the geometrically smoothed new trajectory, which the molecule will now follow. The second illustrative motion technique that we implement is visual motion smoothing. Here we perform temporal blending to show different time steps of the molecule's path at the same time, essentially creating a streak which indicates the speed and the direction of the molecule's movements. Here you can see the geometric motion smoothing in action. On the left side there is the scene without any geometric motion smoothing applied, and you can see that the individual molecules have a more jittery trajectory, whereas on the right video, the molecules move on more smooth trajectories. However, as you can also see from these videos, this effect is rather subtle and not that visible in such crowded scenes. The visual motion smoothing has more impact on the visual appearance of the video, as can be seen here. On the left, once again, we have a scene without the visual motion smoothing applied, whereas on the right, as indicated by these motion trails, we can see that there is actually visual motion smoothing applied. For the context of this work, we are interested in how our illustrative motion smoothing actually affects different scene properties. Here we are especially interested in the effect on story comprehension, as well as speed perception in the scene, and also on the visual appeal of the scene. In related work, trajectory smoothing has been used before, but in another context. In the illustrative motion, in the illustrative time-lapse paper by Lemusic et al., the actual focus elements were subjected to trajectory smoothing instead of the context elements. Here they used time-lapse footage, which led to very fast-moving objects, thereby making it hard to spot the actual focus elements in the scene. However, as we are using footage that is not sped up, we don't need this technique and can instead smoothen the trajectories of the context elements to emphasize the focus on the focus elements which have a more high frequency motion and thereby will stand out in the scene. Motion blur in general has also been studied, but mainly in the context of fast-moving cameras, as can be seen in this example here. However, when we have a moving camera, it will then blur the entire scene, making it near impossible to actually apply selective motion blur as we want to do in our implementation. Motion trails, or temporal blending, as it is called in the fast-forward video visualization by Höferlin et al., uses this technique to summarize surveillance videos by speeding them up and having the temporally blended movements in the scene. In this study, different such techniques were compared, but it stood out that the temporal blending actually didn't lead to the best performance for users, because they were overwhelmed with the amount of information in the scene, and also considered their ability to perceive motion in the temporal blending as rather low. However, in contrast to the scene that is used here, our scene uses many scene elements leading to a crowded scene as opposed to this sparsely populated scene. Therefore, we may see different results. For our study, we did a within-subject study with 108 participants, and we recruited them using a crowdsourced platform called Prolific. For the study, we tested our three main effects of the illustrative motion smoothing, the first one being the effect on story comprehension. Here we asked participants which two molecules, as indicated by their colors, reacted in the scene. In this static image, it is actually quite impossible to do that. However, we know that the brown and the green molecule here would be the reacting molecules. For the scene with visual motion smoothing applied, it's actually also in the static image possible to see, because the focus elements, of course, don't have visual motion smoothing applied, and here the reactants clearly stand out. To indicate which two elements reacted in the scene, users had to select their two colors in this interface, and additionally they also were asked to judge how easy it was to spot the reaction in the scene, ranging from impossible to very easy. For the speed perception, the speeds ranged between a minimum and a maximum speed, which we called the temperature of the scene during the study. Here you can see on the left the minimum speed and on the right the maximum speed. For each scene, users were asked to indicate the temperature of the scene by comparing them to these two baseline speeds. For the speed indication, we once again used a slider where the indicated place in the range between lowest and highest speed the scene temperature actually is. For the visual appeal, we once again added a slider where users could indicate how pleasant it was to watch the video. The slider ranged from horrible on the very low side to very pleasant on the positive side. The results of our study are then also divided up into the three categories, the first one being attention guidance. Here our first hypothesis was that the geometric motion smoothing will significantly facilitate the task by making focus elements stand out from the context. As we can see here in the plots, this is actually not quite the case. The geometric motion smoothing did not significantly increase the correctness. However, for the subjective difficulty, the users reported that the geometric motion smoothing actually made it easier to spot the reactions in the scene. Therefore, we can say that this hypothesis is partially supported. For the second hypothesis in attention guidance, we wanted to see whether selective motion blurring of moving objects, which is the visual motion smoothing, will make the non-blurred object stand out visually. For that, we looked at different visual motion smoothing trail lengths, as can be seen on the left, and here we can clearly see that the correctness improves with increasing trail lengths. However, we can also see that the biggest improvement in correctness actually is when increasing the trail length from our length interval 1 to 2, and for longer trails, the improvement in correctness is no longer significant. The subjective difficulty, as reported by users, also saw a decrease when the trail length was increased. Therefore, this hypothesis is supported. For the speed perception, we hypothesized that increasing the geometric motion smoothing will decrease the perception of speed. We can see here in the plot the different estimated speeds for scenes without the geometric motion smoothing in blue and with geometric motion smoothing applied in orange. You can see that for all the different ground truth speed levels, the perceived speed with the geometric motion smoothing applied was lower than the perceived speed without the geometric motion smoothing, thereby confirming this hypothesis. The second hypothesis in regards to the speed perception was that motion blur may generate the illusion of more quickly moving objects. Once again, here we can see in the plot the estimated speed over the different ground truth levels. In color, we have indicated the different trail lengths, ranging from no trails in blue to the longest trails in violet. We can see that the actual speed estimation decreases for the longer trail length, thereby contradicting our assumption that this trail length would have a positive influence on the speed perception. So this hypothesis could not be confirmed and is not supported. The final hypothesis for speed perception was that increasing the visual motion smoothing would compensate for the decreased speed perception due to the geometric motion smoothing. However, as we've seen, both of our motion smoothing techniques lead to slower speed perception. Therefore, it is not possible to compensate one with the other. For the final category, we looked at the visual quality of the animations in our scene. Our first hypothesis here was that the subjective quality of the scene would be higher with smoother context trajectories. Once again, we can see the different ground truth speed levels on the x-axis and the visual appeal on the y-axis. For the scenes without the geometric motion smoothing applied, the bars are plotted in blue, whereas the plots in orange represent the scenes with geometric motion smoothing applied. We can see in the plot that the scenes with the geometric motion smoothing applied had higher visual appeal ratings, especially for the ones with higher ground truth speed levels. Therefore, we can say that this hypothesis is also supported. For the second hypothesis for visual quality, we expected to see decreased visual quality with increasing visual motion smoothing. However, we can see that the visual appeal actually doesn't seem to decrease with longer trail lengths. To the contrary, at speed levels of 3 or 4, the visual appeal seems to increase with increasing trail lengths up to some point. For the very long trail lengths of 3 and 4, we can then see a slight decrease again. So overall, this hypothesis is not supported. To summarize, we have shown that illustrative motion smoothing can be used to guide attention in crowded dynamic scenes. We also found that users seem to like geometric motion smoothing, although there is no statistic evidence that geometric motion smoothing leads to better task performance on its own. We've shown that the effectiveness of motion trace seems to be saturated at moderate lengths. For trajectories that become longer, the task performance does not increase anymore. Based on these findings, we have come up with a number of design guidelines to be used in conjunction with illustrative motion smoothing. The first one is not to overdo the visual motion smoothing, as we've seen that with our implementation, there seems to be a sweet spot at moderately long visual motion smoothing trails. Secondly, both of our implemented illustrative motion smoothing techniques seem to lead to slowdown effects. Therefore, animation should compensate for this slowdown effect to keep the actual speed at the same level. Constantly fast animations led to poor user performance and story comprehension. Therefore, you should avoid fast animations and maybe adjust the animation speed suitable to the individual scenes. Smooth trajectories seem to be preferred by the users on a subjective level. Therefore, we advise to smooth the trajectories of contextual elements in the scenes for higher visual appeal. Finally, the successful task completion in our study was only at around 60 to 70% for our visual motion smoothing techniques. Therefore, we suggest to add further attention guiding cues such as low lighting of context elements or highlighting of focus elements to improve this kind of task performance. In the future, it would be interesting to evaluate the applicability of our findings to different contexts other than molecular animations. Also, additional studies could be performed to test additional factors such as crowding or varying the heterogeneity of molecules. Our current implementation of visual motion smoothing is done through a video post-processing effect. In the future, we could implement the motion trails in real time to open up the technique to interactive environments. Finally, in the future, it would also be interesting to study the combination of illustrative motion smoothing with other attention guiding methods, to see how this method performs in a more integrated setting as often seen in molecular animations. With that, I'm at the end of my presentation, and I thank you all for your attention.